Welcome back. So we just finished talking about dipole-dipole forces, and now we want to turn our attention to the next kind of intermolecular force, that is hydrogen bonding. So we just finished that example, and now we want to look at hydrogen bonding. So we're still in section 3 here, and we've made it up to page 493, hydrogen bonding. Now remember, this is a type of intermolecular force. It's not a type of bond. Although we use the word bond here, it's not an actual chemical bond. It is stronger than the other types of intermolecular forces, however. So remember, this type of intermolecular force occurs when you have a hydrogen attached to a very electronegative atom. And we're going to limit ourselves in this course to saying that those electronegative atoms that it can be attached to are nitrogen, oxygen, or fluorine. So notice we're taking hydrogen. There must be a hydrogen present, and it has to be attached to a nitrogen, oxygen, or fluorine. So nitrogen, oxygen, or fluorine is going to be the way that you recognize a hydrogen bond. Just because a molecule has a hydrogen does not mean it has a hydrogen bond, because a hydrogen has to be attached to a nitrogen, oxygen, or fluorine in order to have a hydrogen bond. So nitrogen, oxygen, and fluorine, we call that NOF or NOF. So you have to have a hydrogen attached to a NOF in order to have a hydrogen bond in the first place. Okay, so that's how we're going to recognize it. Now, remember, hydrogen itself is one proton and one electron. And so, since there are no other electrons itself, it's using that one electron to share in a covalent bond with that NOF. And so that means the electron is going to be held closer to the nitrogen, oxygen, or fluorine, and that hydrogen atom is going to be kind of exposed. That positive charge is going to be kind of left out there on its own. It's sort of like a naked proton. It's out there by itself with no covering, and that means it's kind of exposed. There's a positive charge sticking out there, and that positive charge can interact with negative charges really well. So what negative charges does it want to interact with? Well, electron clouds a little bit, but electron clouds from other hydrogens attached to NOFs is what it's going to interact with the most, and we call that the hydrogen bond. Now that exposed proton, which is a very strong positive charge, is going to attract the electron cloud of the other parts of other molecules that are more negative. So imagine you have a situation like HF here, and that hydrogen is attached to a NOF, to a fluorine in this case. And so that means we can have hydrogen bonding. So notice the one side of the molecule is hydrogen, the other side is fluorine. And so that hydrogen on the one side is going to be slightly positive, and the other side of the molecule is going to be slightly negative because fluorine is very electronegative. And that means you have this almost like a dipole moment created here. And that's going to cause these molecules to interact with one another very strongly, more strongly than a dispersion force or a dipole-dipole force. So water exhibits this type of hydrogen bonding very well. And look, we have a hydrogen and it's attached to an oxygen. So we have two of those actually. And that means we're going to draw the hydrogen bond from that hydrogen attached to the oxygen as a dotted line across to the negative part of another of the same type of molecules, which happens to be the oxygen part. So this is how we draw a hydrogen bond, a dotted line from the hydrogen that can exhibit hydrogen bonding, from the hydrogen attached to the NOF, to the NOF on the other molecule, or in this case, we're talking about oxygen, right? So from that hydrogen to that oxygen, from that positive proton to that negative region of the electronegative atom on another molecule. And notice, water does this really, really well. It makes a series of hydrogen bonds, holding it together in a very interesting and complex way. Hydrogen bonding is another type of intermolecular forces and a very strong intermolecular attractive force, stronger than dipole-dipole and stronger than dispersion forces in general. So that means substances that have the ability to display or to undergo hydrogen bonding in general are going to have higher melting points, are going to have higher boiling points than other substances that don't have the ability to do hydrogen bonding. Okay, now it's important to note, these are not actual bonds, as I keep saying. They're not chemical bonds, we just call them bonds. They're only 2 to 5% of the actual strength of a covalent bond, which means they're very, very weak compared to real chemical bonds. but they're still a lot stronger than other types of intermolecular forces, such that they play a pretty big role. Notice here we've got ethanol and dimethyl ether, and each of these have hydrogen, but you have to have a hydrogen attached to a NOF in order to have hydrogen bonding. So notice in the ethanol formula, you've got that oxygen and you've got a hydrogen attached to it right there. So ethanol can undergo hydrogen bonding. And in dimethyl ether, we've got a carbon attached to the oxygen attached to another carbon. So even though there are hydrogens present, they're not directly connected to a NOF, or to oxygen in this case. And so dimethyl ether does not undergo hydrogen bonding. Okay? So ethanol does, dimethyl ether does not. What about their molar mass? About exactly the same. And therefore, they have the same dispersion force. Their surface area, approximately the same dispersion force. Okay? So the main contributor here is the hydrogen bond itself. And notice we draw that bond between the hydrogen and the oxygen, or the electronegative atom of the other molecule. Okay, notice the difference in the boiling points here. 78.3 compared to minus 22. So that hydrogen bond is pretty effective at creating a lot of attraction, which is why we refer to it as the strongest type of intermolecular force you can have. So notice here, as the period increases, we see the boiling point changing based upon the ability to undergo hydrogen bonding. So these three do hydrogen bonding, this one doesn't really, and so the boiling point is higher on these three than it is on that bottom one, because of the ability to do hydrogen bonding. And that plays a huge role in intermolecular forces. One of these compounds is a liquid at room temperature. The others are gases. Which one and why? And how would you actually know? Remember, we said the phase that a substance is in relates to the intermolecular forces that are present. So what I want to do is go through each one and identify which ones have which intermolecular forces, and the one that has the most is the one that's likely to be a liquid at room temperature. The others can remain gases because they don't have an attraction that keeps those molecules sticking together. So first, we're going to determine the kinds of intermolecular attractive forces. Formaldehyde, our first molecule on the left here, has dispersion forces. Yeah, it has electrons, so it should. Actually, they'll all have dispersion forces. This one has a dipole, so it has dipole-dipole forces. And it has hydrogen, or it doesn't have hydrogen bonding, because even though there are hydrogens, they're not attached to a nitrogen, oxygen, or fluorine. So it has two of the three intermolecular forces we've looked at so far. Okay, what about fluoromethane? We've got the dispersion force, and its molecular mass is a little bit higher than in formaldehyde, but not a lot. It's tetrahedral, so it's kind of a particular shape, spherical shape. It has CF bond, a CF bond that is polar, and so it would have dipole-dipole forces. And even though there are hydrogens, they're not attached to a NOF, so there is no hydrogen bonding. So we're predicting here that it would have about the same intermolecular forces as formaldehyde, maybe slightly more because it's higher molar mass and because fluorine's more electronegative, and so slightly more dipole-dipole force, but their boiling points are going to be very similar. If I had to make a call, I would say fluoromethane is probably going to have a slightly higher boiling point than formaldehyde. Now what about this last one, hydrogen peroxide? We've got dispersion forces about the same as fluoromethane, and it's in a tetrahedral bent shape. And so it also has a dipole-dipole force, which is uncancelled. Even though it's written in a straight line, it looks like the dipole forces would exactly cancel. Remember, each of those oxygens have lone pairs, have two lone pairs around them, which makes them bent. So they're tetrahedral in their electronic geometry, but they're bent in their molecular geometry. So each of those oxygens connect to the hydrogens in kind of a downward way. Remember, they've got the two lone pairs, and then they would be connected. So they can have dipole-dipole forces. And we have hydrogen, but it's attached to an oxygen. So that's part of the NOF, and that means we can have hydrogen bonding. So this molecule, hydrogen peroxide, has all three types of intermolecular forces we've discussed. And therefore, we're going to say overall that in comparison, since we know hydrogen bonding is the strongest type of intermolecular force, that ultimately the hydrogen peroxide itself, which has the additional hydrogen bonding attraction, should be the one that's liquid at room temperature. Hopefully that makes sense. Choose a substance in each pair that is a liquid at room temperature, the other is a gas. Now, here we're not given the structures, we have to come up with them on our own, but that's no big deal because we know how to draw Lewis structures and how to come up with a three-dimensional shape of these molecules. So we're really looking at all of the forces together and sort of comparing. And notice if we can identify one that has hydrogen bonding, we can predict then that it has a stronger intermolecular force than the other one. So instead of having to draw out the three-dimensional structure and figure out, does this have dipole-dipole or does that one have dipole-dipole, we notice immediately, oh, can it hydrogen bond? If so, it's a stronger intermolecular force than the other one. So we pick the two. Notice all the molecules here on this slide have hydrogen, but not all of them can do hydrogen bonding. That's a key distinction. You've got to have hydrogen attached to a NOF. Remember that. Now, how does this affect how these molecules actually behave in different substances? And what other things do we have going on here? We're going to look at how these attractive forces relate to the solubility of particular molecules. Remember the old saying, like dissolves like. That is, if they're both polar, they're going to dissolve each other, or they're going to be mixable or miscible, as we often say. And if one is polar and one's nonpolar, they're going to want to separate. So miscible liquids will always dissolve in each other. They'll be mixable, and like will dissolve like. A nonpolar and a nonpolar, they'll have good interactions, and so they'll mix up really well or be dissolved in one another. It's hard to think about a liquid dissolving in a liquid, but sometimes those are the words we like to use. So polar substances dissolve in polar solvents, and nonpolar in nonpolar, and so on. So you want the intermolecular forces to be similar in order for the something to dissolve in something else. In the case of liquids, in order for them to mix well, they have to have similar properties, similar intermolecular forces. So here we have immiscible liquids. That means liquids that don't like to mix with each other. So we have pentane, a nonpolar molecule, and water, a polar molecule. We mix them together. Since they don't have similar intermolecular forces, they're going to form two layers, and they're going to want to be away from each other. Right? Think of it as these pentane molecules on top here cannot break down into the water layer because you have all these hydrogen bonds happening in the water layer, and you don't really have any of those happening in the pentane layer. So to get one pentane molecule down into the water, it would have to break up all the positive attractions that those water molecules have for each other that keep them together, and pentane is just not capable of doing that. So therefore, they're immiscible liquids. They don't mix together. Okay, notice here in this situation, we've got the water molecule, and we would expect something else that has similar properties, like methylene chloride or dichloromethane, however you like to say it, which is a polar molecule, should be able to be miscible and mix. Something like ethanol or ethyl alcohol has hydrogen bonding. We expect it to mix well with water because they have very similar properties. They're both polar solvents. Okay, and nonpolar solvents, for example, also like to mix together. Now here's another type of intermolecular force we like to consider, but it's not really anything completely new. It's just a force that happens when you have an ion and a molecule that is a dipole. Okay, so notice we've got sodium and chlorine here, and these two ions are table salt dissolved in water. And remember, we've talked about water can dissolve table salt really well because it can have nice interactions between the negatives and the positives and the negatives and the positives. And that means the water can slowly break off one ion at a time off of the salt cube itself. So it has strong forces, strong enough to break up the crystalline lattice of the sodium chloride because of this ion-dipole attraction. So it's kind of like a dipole-dipole force, but since we have an ion and not another molecule that has a dipole, we call it an ion-dipole force, or an ion-dipole attraction. And that causes a solubility for this molecule to a large extent. Choose a substance in each pair that is more soluble in water. So what is it that we know about water? polar hydrogen bonding, and so therefore the substance that's likely to be soluble in water is also going to have similar characteristics. So this one on the left here is methanol, and notice it's got this OH group, that's hydrogen attached to a NOF, so it has hydrogen bonding and it's polar. So that's good news for it. We expect it, since it can do both of those things, to be the one that's soluble compared to this one. Notice these two fluorines are attached directly to the carbon, which is also attached to this hydrogen and that carbon. And so it might be polar a little bit to where these two fluorines are, but it doesn't undergo hydrogen bonding. So we're going to pick the left one here, methanol. How about this bottom one? Notice a long chain. 1, 2, 3, 4, 5. This is pentane here. And we have this molecule, which has 1 chlorine and 3 hydrogens. So this one's long, has a lot of surface area, has a high dispersion force, but it's nonpolar. That means it's not going to mix with water. And it doesn't have hydrogen bonding. Okay, how about this molecule? We've got hydrogen, but it's not attached to a NOF, so it doesn't have hydrogen bonding. But there's one, what we call a heteroatom, an atom that's different, a chlorine here instead of another hydrogen. That means it is polar, so it's more likely to be dissolved in water than this nonpolar molecule is. So we pick those two based upon the intermolecular forces. All right, so kind of a summary. What we've seen for intermolecular forces so far. Dispersion forces are the weakest. Dispersion forces, or London dispersion forces, are the weakest of all intermolecular attractions. They occur in anything that has electrons, which is all molecules and atoms. And the magnitude of the dispersion force increases with molar mass, meaning higher molar mass is more number of electrons, and also surface area. Okay. Polar molecules can have dipole-dipole attractive forces, or dipole-dipole interactions. And dipole-dipole forces are slightly stronger than dispersion forces in most cases. And something that has both of those types has more intermolecular forces than something that only has one of those types. And we have hydrogen bonding, which is the strongest of all the intermolecular forces. It happens only when you have hydrogen attached to a highly electronegative species, like nitrogen, oxygen, or fluorine. We're going to limit ourselves to those three, the NOF I talked about before. And so a substance that can undergo hydrogen bonding, being the strongest intermolecular force, is going to allow then that molecule to have more forces than any of the other types, more attractive force than any of the other types. Okay. Ion dipole forces are also present, can be present when you have an ion dissolved in a polar liquid, and that can contribute to the amount of mixing or dissolving that something can do, and also lead to a strong intermolecular attraction. Okay, we have a pure electronic charge, positive or negative, in that ion, and that can interact directly with that separation in charge on the dipole of the polar molecule. And so that's very strong attractive forces between two oppositely charged things. Okay, so these are really important in compounds, solutions of ionic compounds like sodium chloride or table salt dissolving in water, and that helps us to explain a lot of those things. So here's table 11.4, which you'll find at the bottom of page 495, and notice the strength is increasing as you move down for these different types of intermolecular forces. Now, we finished we finished section 3. We want to move into section 4. Now that we know all the different types of intermolecular forces that can happen, what difference does that make in the molecule or in the substance? Instead of just saying, oh, it affects the boiling point and the melting point, what other things does it affect? What practical differences do we see between different samples? That's what we'll explore next. We'll look at in more detail.